You really nice.
We're talking about you, right?
All right. So, welcome everybody. This is the Rocketry 101 workshop, or 101. And so, for the next 2 hours, we're going to go. Basically, there's two parts. 101 is going to be a very basic overview of liquid rockets. It's not a design course. It's not like you say you get the engine. It's going to be like, hey, this is what propellant combinations are out there. All right, just to get just a really overview. It's almost like a survey. Okay. Now the second part is going to be a little more detailed. I think for the first half, Purdue's going to go over basically their journey from having no liquid rocket to a liquid rocket in a very short amount of time, and kind of going over what's going on with that. And then San Diego is going to go over Colossus fluid systems. So up here you have Kyle Runkle. He is our fluid systems lead for Purdue. We have Jack. He's now the ex-president of SEDS for San Diego, and Andrew. I don't know what we do. I've been in fluid this guy. I just met him.
I'm the equivalent of Kyle for San Diego, so fluid systems lead.
And don't be afraid to ask questions. I can say I'm talking. Just shout, ask questions, raise your hand. I don't care. This is supposed to be a very informal. Say this is what liquid rockets are going on because they are very intimidating. They are crazy, and so ask questions. Okay. So. Are we doing the comments first?
You want the comments first?
We can do whatever you want first. Whatever you have there.
There we go. Okay.
That's the next thing. That's the next presentation.
So you want the comments first then? Yeah.
Okay. Okay. So we're,
Yeah.
this is good. This is great. Okay. I thought there was something else before this. All right. Perfect. So I'm talking first.
Yep.
Okay. So we're going to go over propellants. And again, this is not a design course. This is purely, hey, this is what's out there. Okay.
Interesting slide.
Yes. This is.
Okay.
There we go. Cool. All right. Neat. See the next slide. Actually, no. Okay, this will be fun. Again, yeah. This is not a design course. Speak up. Cool. So we're going to go over engine basics on some pros and cons of various fuels and oxidizers. The idea is that when you guys go back to your home school and you say, hey, let's do this liquid rocket, you can say, if someone says, oh, let's use hydrogen peroxide, well, you can say, well, maybe we can, but here's some other options and here's some things that go on with it. And so as we were talking, I'm sure Kyle and I will be giving some tidbits and stories about things. If you got some keep time, because we'll ramble on a lot. Okay, and some other things. So, next slide. So some basic things, I'm sure everyone in here knows how physics work, right? Second and third law, that's how you go. So a couple things we talked about though is ISP. ISP is essentially a measure of engine performance. It's measured in seconds. And so a typical value of ISP is anywhere from 170 for solids and 350 for liquids, and then higher if you're SpaceX and Blue Origin. But basically, if I say an ISP or a number like that, it's essentially a measurement of performance. It's thrust over. It's basically how much thrust can you get out of a unit of mass. Okay. So if rocket's the rocket equation, right? So you double your mass, you're not doubling the size of the rocket. You're exponentially getting the rocket size. So you want to know, okay, if this mass is going to give me how much? That's what ISP is essentially. And then OF is just the oxidizer fuel ratio. One reason I'm bringing it up in this conversation here is that when you're sizing a rocket, okay, if you know you need 10 pounds of oxygen, great. How much fuel do you need, right? And so that's kind of a typical ratio of okay, if I need this much of oxygen or oxidizer, I need this much of fuel. And so you start sizing your rocket. Okay, that's the first thing you gotta do when you do rockets. I know a lot of people, us included, definitely us included, we spent 4 months going around in circles trying to optimize all these different tank geometries and materials. No, you need to get your thrust and you get your weight. All right, you get your weight from how big your tanks are. That from your ISP to your OF.
Yeah, O to F, there's a lot of things that will go into that. Your biggest limiting factor when it comes to picking what your O to F is for whatever fuel propellant combination you've got is the combustion temperature. The closer you are for a propellant combination to what's called stoic, it's where all of your oxidizers reacting with all of your fuel in complete combustion. The hotter the combustion is going to be, and the more efficient the engine is going to be because the exhaust is going to be traveling out of your engine that much faster. However, then you're hitting up against limitations when it comes to the design of your chamber and injector and as to if they can actually handle those temperatures. So for example, for the Purdue SEDS rocket, stoic for LOX methane is an ODEF of 4. However, for the Purdue SEDS liquid rocket, we're at an ODEF of about 3 because just with our engine design, we can't handle the temperature going all the way up to an ODEF of 4.
Yeah, when you start designing these engines, if you want to use stoic for general, that's fine. But when you guys get to actually doing things like this, if you try to get your engine to be stoic, you'll not have an engine at the end. And if you stay to the next, the 201 workshop, you're gonna see exactly what I'm talking about, okay? And how hot 5,000 degrees really is. All right, move to the next slide. All right, so, wow, this is a lot smaller than I thought. I thought I was gonna get on a large thing, so you can't read any of this. But San Diego's gonna go in detail over a fluid system later. But essentially, preview, this is basically everything we need to launch the LOX methane rocket we have.
This was a year of my life right here. Is what you're
And so, actually, go ahead, Kyle.
Yeah. So what you've got here for
Real quick overview, yeah.
yeah. So obviously you got the rocket over here. For percentage, we used coaxial tanks in order to help save our methane a little bit. But basically, what you have in general for a fluid system is you've got some kind of pressure and gas. You've got an oxidizer and you've got a fuel. For Purdue, what we had is we used dual cryo. We had liquid oxygen as our oxidizer and liquid methane as our fuel. And so one of the complications that we had with that is we wanted to use pure methane, just because kind of we want. Yes.
You mentioned dual cryo. Some people might not know what that means.
Okay, yeah. So basically, both the oxidizer and the fuel are cryogenic. When it comes to cryogenic fuels, your only real option as a student group, if you can get to that, is liquid methane or LNG.
We'll get that in the
liquid hydrogen, yeah, you're not going to use liquid hydrogen as a student group unless your group wins the lottery.
Yeah.
But so for this, what we use is we basically used a liquid nitrogen bath to convert gaseous 5,9 methane into liquid methane before loading it into the rocket. So that's what this system is here. It uses the liquid nitrogen. You're going to need some kind of nitrogen supply for operating all your valves, any kind of purges in order to keep things safe and clean when you're not using them, or to purge through afterwards. And then for actually on board the rocket, most teams will use, or a lot of teams will use helium instead of nitrogen. It's more expensive, but you're saving the weight since helium is just lighter than nitrogen.
And I know right now, this is like, what? Seeing a PNAD for the first time. Again, San Diego, we're going to go over much more detail later. And this is just kind of a preview. So, it's different than solids. It's not, you don't mix cryo-oxygen and cryo-methane and freeze it and put it in a metal casing. It's a lot of fluid and a lot of plumbing laying out. So, the next slide. Cool. So, real quick, so we're talking about this and you're making your decision, hey, what's out there. There is no like safe or best option. Of course, like hydrazine that can kill you, or nitrogen.
Don't use hydrazine, please.
Yeah, like that will kill you pretty quickly, right? But like those are, but like the common propellants, like we're gonna go over, there is not a best option. There's not like, oh, everyone needs to do this and that, because it all depends on what you have, we have access to. Out in Lafayette, it's a little hard to get hydrogen peroxide. If you can, it's expensive. But it's shipping is like $2,500 alone just to get a barrel to West Lafayette. But if you're in Texas and you live right next to the plant, well, it's going to be a lot cheaper, right? Variables like that and all kinds of fun stuff. All the comparative we're going to be using, like it's better. It's all based on what we're talking about. There are some propellant combinations that are crazy efficient, but like are going to kill us if we touch it. So like we're not going to talk about those. And yeah, perform are reasonable. So the next slide. So next one again. Oxidizer. So again, every rocket engine needs an oxidizer and a fuel. All right, those two come together. We get combustion. Combustion creates pressure. Pressure pushes things out. Then physics takes over, right? And so we first need to carry our oxidizer. Okay, so of course our favorite one of all is, well, my personal favorite for practical things is liquid oxygen. Kyle, you want to go with liquid oxygen?
And first, we can take a pause. Can you guys in the back kind of slide over, and if we can get more of the people to kind of slide over along the back? We've got people on their tiptoes out in the hallway.
And this is 2.5, almost 2 hours, so I'm sure some of you are going to try.
And I guess also some people want to maybe sit down in the hallway, I guess, if that's a safe thing to tell people. Yeah, and then we've got some space right here in the front. If some people want to come kneel down in front.
We're not going to bite, guys.
Yeah. Okay, so yeah, so liquid oxygen, that's a pretty universal, that's a pretty much an industry standard to use. You can't really get a whole lot better in terms of an oxidizer than liquid oxygen. When it comes to efficiency, I mean, from an experimental level, liquid fluorine's a little bit better, but you're not going to use liquid fluorine as a student group. Yeah, just don't. It's very toxic and very expensive and very bad. So yeah, so liquid oxygen, its main con is that it's a cryogenic, and there's a lot of safety factors that come along with liquid oxygen. So if you are looking into doing a liquid oxygen system, the best guide that I can tell you to look up is there is an ASTM standard for designing an oxygen system.
Or talk to Larry back there. Larry is NASA Stennis.
Yeah, Chris, can I talk about 5 minutes?
Not,
Or you got,
not 5 minutes, but we can.
okay, look, we are here to let you know that we have a video that's 12 hours long that deals with the hazards of working with liquid oxygen blocks and also gaseous oxygen. And if you're using oxygen as an oxidizer, you need to talk with me before you leave, okay? I've got the forms right here that you can fill out. So, and we would send a flash drive with 12 hours worth of video training about using locks. It won't cost you anything.
Well, highly recommend talking to them. Oxygen, very crazy. It's very, very specific in terms of the materials you want to get and the cleanliness standards you need to have, and all kinds of safety standards with regards to how you want to use it. For example, one of the crazy things about liquid oxygen, if you have liquid oxygen that saturates some kind of carbon material like asphalt or wood, then you are it's at risk of what's called impact ignition. If you were to say drop something like a wrench on that asphalt that's saturated with oxygen, it can actually detonate. Liquid oxygen's a pretty crazy thing.
Yeah, and if you get, let's say, a dirty fingerprint inside your locks line, or you have bug crawls in there, your line can blow up. Okay, so it has to be super, super clean. And so the video that he's talking about is your safety procedures, and it's not going to tell you how to clean things. I mean, I haven't watched the whole 12 hours, maybe it does. But it goes over like why things need to be, that type of things need to be taken into account. Because oxygen, okay, yeah, we breathe it, great, but when it's in liquid form, it's, it can be dangerous stuff. All right, it's not a toy to play around with. It's not, let's just squirt some oxygen in the edge of it. No, it's dangerous.
Well, it also has the pieces of the components and everything else, the individual components and the materials that they're made out of. It has an introduction to that tool that you can use to go in and be able to pick out the right components to be able to insert into your line.
Yeah, picking the right material is important with liquid oxygen. Like for example, titanium. It's pretty popular, kind of space age alloy. It'll burn pretty easily with the pure oxygen, not even necessarily under pressure. It'll want to burn. So yeah, it's definitely a good option. You're going to be hard pressed to find an area where you cannot get a hold of a durable liquid oxygen. It's used in a lot of different industries, so this is not one you're going to have a whole lot of issue getting a hold of. It's also not necessarily going to be super expensive to actually get the propellant itself.
But the equipment might be expensive though. Okay, because you can't just use a regular solenoid valve from RC Hobbies. They have to be specially serviced, and especially even the seals in there. If the seals aren't the right material, things can blow up, break, crack, all kinds of things. And so cryogens, they're really efficient. They're also a little complicated, also a little pricier. Again, I say pricier. There's a lot of variables into things, but again, super minimal. Next slide. So hydrogen peroxide. So most of you bought pricing hydrogen peroxide in the store, right? You maybe put on a cut or something, right? That's like
3%.
3%.
Yeah.
High test peroxide is like 90, 98. Okay. Now, what's fun about peroxide is that it's storable, so it's not cryogenic. So it means when you leave it in a container, it's not going to disappear if you just leave it there, right? It will decompose a little bit.
And if you've got a container that's built for it, you can keep hydrogen peroxide stored in that container. It's not going to decompose very quickly at all.
It's probably moderate in there. Yeah. The density is a little higher than LOX. That's always good, right? And there's no cryo collapse. So we didn't talk about this. So if you have a container of a really, really cold fluid, let's say LOX, okay, and we're going to put some warm helium into it to pressurize it. Well, we can calculate how much gas we need to push out a certain amount of fluid. Well, the problem is with cryogens, it doesn't work exactly like that because the helium won't condense, but it gets a lot denser, right? And so we call that cryo collapse. And so even our rocket, which will go about in the next half of this presentation, we had, 26 pounds of liquid oxygen, all right? We can't even, it took many, many iterations, and we're still iterating to figure out how much helium we actually need to get that to where we want, the pressure we want.
I'm going to grab you a little bit first. I actually got corrected by Scott on this. Cryocollapse is a very specific thing that happens when you're trying to use nitrogen to pressurize LOX because the saturation curves actually will cross. So you can get, if you're trying to pressurize LOX with nitrogen at higher pressures, you can get some weird phenomena going on, which is another reason to use helium to do oxygen pressurization. But it's for when your helium density is dropping. It's not cryocollapse is specific for when you get that saturation curve crossing. But no, Scott's corrected me on this.
Yeah.
I wanted to
Scott's right.
make sure. Yeah.
But yeah, cons, it's hard to get. Like I was saying earlier, it's like $2,500 to ship 1 barrel of hydrogen peroxide from Texas to West Lafayette.
Yeah, there's not many places that'll make it at this concentration.
Yeah.
Just because
There's
there's
like
not a lot
one.
of applications for it.
There's like one in Texas. Special storage considerations. Yeah, it's storable, but like it does decompose. It can rapidly. It could just, if measures aren't taken, there are scenarios where it can be sitting there and all of a sudden it blows up because it decomposes and it gets hotter, which decomposes more and more and more, and all of a sudden you get an explosion. Okay. So experienced mentors aren't as common. Like there's no 12-hour safety video on hydrogen peroxide. And you probably need a catalyst bed. So basically, if you take hydrogen peroxide, okay, we run it through either platinum screen or whatever.
Or silver.
Your silver, and we split it up into basically water and oxygen. And take the oxygen is actually doing the combustion, so we're still carrying ox. We're just putting it somewhere else.
Yeah, so leaving that peroxide bed, if you're saying you're decomposing 90% peroxide completely, it'll be about 1400 degrees Fahrenheit leaving the catalyst bed.
Yeah.
It gets pretty hot just leaving the catalyst bed. And so you'll flow that in, you'll react it with whatever fuel. If you use an RP1, one of the nice things about using hydrogen peroxide is if you're decomposing 90% peroxide completely and getting that 1400 degrees, it'll auto-ignite with RP1. So you don't need to worry about having another source of ignition in order to get things going. If you start flowing the hydrogen peroxide and get it up to that temperature and you put in your fuel, it'll auto-ignite with RP1.
And Kyle and I are already running out. So we're going to pick up a little pace a little faster, but please free to ask questions again. So next one, nitric oxide. Honestly, we don't have anything hands-on. So we've had hands-on experience with everything you've seen here except this.
This is a pretty standard selection for newer teams coming in. It's easier to get a hold of. One of the nice things about this is that you can use it to kind of self-pressurize. Just heat up the tank, it'll boil and pressurize itself. It's very popular selecting with hybrids as well as with use of other simple fuels like ethanol. So if you're just getting in, this is a very good, easy, cheap selection. It is not a very efficient selection.
Another thing too, just because, it's nitric oxide, people use that in cars, it must be safe. It's not safe, okay? Don't assume it's safe. The fuels, okay, when we get to ethanol, which is moonshine, okay, fine. But don't assume any oxidizer is gonna save, all right? That's when you kill yourself, or blow an arm off, or whatever, okay? So don't do that.
Don't do that.
I think we're on the fuels now.
Yep.
Yeah, keep on going. All right, cool. Alcohol is perfect. So again, easily accessible. If you're over 21, there any bottle shop you can go to.
Go pick up a bottle of Everclear. You've got your rocket fuel right there. You got some left over. Have a decent.
University of Michigan has a nitrous oxide ethanol rocket, so it's literally laughing gas and alcohol, which is great. Little environmental concerns. If you dump it on the ground, it's not a big deal, right? Cons. People have done these engines before. Like with Vox, there is tons and tons and tons and tons of papers and data and experiments and hey, this is what we did with this thing, which we pretty much similar to what we were doing, right? Here's some data on it. With alcohol, it's out there, but it's definitely a lot harder to find.
Mm-hmm. There were some past actual academic and government efforts to use ethanol as a fuel, but there weren't that many, and it's mostly nowadays used as entirely on the amateur side of things as a fuel for rocket engines like this. So there's really not a whole lot when it comes to actual scientific research on some modern designs for it.
Yeah. And again, I'm not expert again. This is an overview. I mean, we could go into detail on each one of these little ones, but it's alcohol, right? It's that type of deal. All right, next slide. We got 2 more slides. So kerosene. Everyone's heard of kerosene, right? Falcon uses it, Falcon uses it. So the good thing about it, tons of data. There's tons of data on Vox RP1 engines. It's everywhere.
Mm-hmm.
It's durable. It has some good thermal properties.
It's also very dense, so you don't need quite that large of a tank in order to hold as much as you need, which is very helpful if you're doing pressure fed.
Some cons, some things it finds really hard. How easy for you guys to get RP1?
We quoted it for $2,500 shipped from Texas for a 155-gallon barrel.
Nice.
I was like, no.
It's almost exactly like hydrogen peroxide was. Yeah. Those are expensive. Yeah, go ahead.
So that's RP1. Kerosene is unrefined. Do you recommend avoiding unrefined?
Doesn't matter.
You can use Jet A. Just go to the airport with a gas can.
Yeah, there's all kinds of different
Same as
refinement.
RP1.
There's all kinds of different refinement levels for kerosene. RP1 is, rocket propellant 1. It's the standard that's used if you're using kerosene in the aerospace sector. But if Jet A, that's a lot more. It's a lot easier to get your hands on, and it's a pretty refined. It's not quite as refined as you get with RP1, but it's got some pretty good quality to it. So that'll do. Especially if you're just getting into it, that'll probably do just fine.
And Russ brings a good point too, in terms of how much quality of the repellent. Right now we're using 99 point. How many nines after the point?
9.5 methane is the gas bottle.
Yeah. So we have 9. There's 5 nines after the point for our methane we're using in our engine. Guess what? We don't need anywhere near that. Okay? Because no matter how well we think we designed our engine, we're all students here, guys. We're learning. This is a learning experience. We're not professionals. We're getting there. We're not professionals. You know, it's the first iteration we did. The thing I'm gonna go over in a few minutes. You know, we don't need those 5 nines on it. We could have gotten with 70% liquid natural gas and been just fine because you know, you learn things along the way. And yeah, so yeah, Jet A is probably just gonna do it. All right, cool. I think it's the last slide. Two.
Methane.
So methane, do this kind of.
Yeah, so methane, when it comes to gaseous methane, if you're going to try to liquefy it yourself, if you're only using a small amount, it's not that bad to do a liquid nitrogen bath. You just have to keep the nitrogen pressurized at least 100 psi. That's where you get the boiling temperature of nitrogen such that it's not going to freeze the methane if you've got it in a bath. If you go lower pressure, then I think it's like 90 something psi, you'll get to the point where the nitrogen is cold enough to actually freeze the methane solid. You don't want that to happen because then you're stuck waiting for it to melt. And we've had that happen.
I think SDSU found like a giant thing of liquid natural gas that hooked it to the back of a pickup truck and just tapped it on there. Honestly,
so
that's a good way to go.
Luckily, liquid natural gas, there's a lot of places now that will supply that in the U.S. Because there are some bus systems that are starting to use liquid natural gas in some urban areas. There's also some applications when it comes to liquefying it to put it on ships to go to a port. So you could get lucky. I know there are some areas where Praxair will offer liquid natural gas dewars. And so it's something to look into. It's basically you'd get it in the same format. You'd get it a LOX. You'd just get a dewar of the liquid natural gas. You're not gonna get like 5.9 purity unless you really want to shell out for something specific from Praxair of liquid methane. But LNG, you can get pretty high quality LNG and 93 to 95% methane. And I mean, it's not like that other 5% is stuff that's not going to react. Most of that is just other hydrocarbons. So you're going to be probably no worse off really using that compared to pure liquid methane.
Purdue has an AAA paper on the condenser. So we're talking about Purdue, of course we use methane. It's only because of the competition, again, I'll get to in a second. But we condense it to liquid methane ourselves. And so he's talking about condensing it. All right, I think just one more slide left and we're at negative -1 minute. So yeah, real quick, let me picture this. These aren't exact data. This is purely guesstimates I did in a coffee shop. Not guesstimates. These things off the top of my head I did in a coffee shop. All right, but the idea for this graph here is that when you size your rockets, get an idea, right? I mean, it's about, if you have 10 times as much oxygen as the fuel, you've done something wrong, okay?
Yeah, so when it really comes to selecting your O to F, when you're trying to optimize for efficiency, you want to get the value as close to stoic as you possibly can. For a student rocket, you probably don't want to try to play in your hand with doing something ox-rich, so you're more than likely going to be having a fuel-rich engine of some sort. And it really comes down to, with your design, what kind of temperatures can you handle. We're doing ablative for our engine. We don't have film cooling, it's just the ablative. We do an O to F just under 3. That's like 2.94 is what it actually comes out to. Stoic there is a value of 4. And so the closer you get to stoic, the hotter it's going to be. When it comes to rocket engines, the hotter the gas is in the combustion chamber at the same pressure, just because of the fact with the converging diverging nozzle, the speed that the gas is coming out of that is really subject to the temperature. Because if you've got say a standard converging diverging nozzle, maybe you've done really in-depth fluid mechanics yet, or aerodynamics, but if you've got a converging diverging nozzle, if you got it so that when you choke it down, the flow down, it hits Mach 1 at the choke. When you then re-expand it, the flow will keep speeding up, and that re-expansion is going to be a function of the pressures that you're seeing in your expansion area, and it's in terms of the Mach number. So if you've got a set system, a set chamber pressure, a set throat area, a set fluid, if you increase the temperature of the fluid, the speed of sound goes up. The Mach values will stay the same, but because the speed of sound is going up, the speed of the fluid itself is going up. So the hotter the gas that you get inside that rocket engine, the more efficient you're going to be. It just comes down to you want to make sure you're not going to melt your engine.
How do you all account for the varying atmospheric pressures, or how do you keep it in those?
Yeah, so basically what you want to do is you'll want to select somewhere kind of in the middle of what your projected flow. We're going to size it so we're perfectly expanded here. You can definitely find papers online about suggestions on how to specifically figure out where it would be most efficient to size it. But generally, you're going to start off, at sea level, a little
for larger vehicles. What we did for the Purdue rocket, I hit at one point, at 10,000 feet, this is it. Like, in retrospect, if we get 10,000 feet, we'll be happy. right? So like, it's get it close. I mean, for what we're doing, again, it's a learning experience. It's our first engine too. We just did, and we were all like, oh, we get exactly. We got to be at 15,000 feet. That's when no, just sea level's good for now. And we go more in depth and I do a lot of stuff in other classes. Our part's out of time. I think by the end of the slides.
Yeah.
Cool. Okay, so they're gonna go over. I forget what you guys over. I know it's still 101 stuff, but
The Colossus.
yeah. Cool.
We can go over here.
Isn't Colossus the second part? Reading that now.
You want us to?
We don't have anything on the call.
Yeah.
Well, we can do the other slides for them.
Yeah, okay, sure, we
We'll
do
go
that.
to the other.
Oh, we still don't have. So, split in two parts though. We have this one, and then who's doing this next, the next hour?
You can go ahead and do it now.
It was all integrated. It was changed. It was all integrated into one.
Oh, really? Oh, cool. All right, neat. So this is like story time. I'm gonna.
Okay, before we move on for propellants, though, does anybody have
Oh, yeah,
questions?
point. Yeah.
Semi-seriously, what do you guys think about aerospikes? You're talking about pressures?
Aerospikes are something that are still very experimental. You obviously you have NASA's linear aerospike from the SSTO days. You do have some research institutions doing the radial aerospike. With the radial aerospike, there's still issues getting the materials such that you're not melting that tip. Aerospikes are definitely up there in terms of complexity and getting a cooling system such that you're not going to melt that aerospike. I mean, if you think you can pull it off, then obviously you get the advantage of being perfectly expanded over a range of altitudes rather than at a set altitude. But that is also something that is a rather hard thing to pull off and isn't something that has actually been used in a successful commercial vehicle of any kind.
Yeah. Look up Ark in Space if you want a nice read. If he's not in prison again. Okay. Okay, so I had a lot of half hour for this, so I go over. Just let me stop. If you want to stop ahead, just let me know. Okay. Cool.
Are there any other questions?
Yeah, any other questions on liquids? Yeah.
What's the hardest part about starting a liquid fuel rocket program?
Everything.
Everything.
Oh, actually, it's what the whole thing took me out. So I kind of go over all of our difficulty in this next little bit here. But honestly, if you want to pick one.
It's very hard to figure out where you're going to start in terms of when you're first starting off. It's hard to figure out where you want to even go to get the information that you need. That can be a little bit of a hunt sometimes. Luckily, we had the Zucrow Propulsion Lab at Purdue, so we had people there that kind of do this thing pretty regularly at this scale. So we had a lot of people that we could go and ask questions. And yeah, I know both when it comes to our program as well as I can tell you for UCSD, if you guys have questions and you're doing these kind of liquid rocket programs, we'd be happy to answer any questions you guys have when it comes to help getting started. We love doing this kind of thing, so
Yeah,
we'll be more than happy to help out.
We're gonna get to you.
Do you guys think you play a little safe with choosing methane and LOX for
We
your
did not choose that statement.
The reason we chose that, I don't know how familiar you guys are with the Farm
I'll go
Mars
to the slide.
competition. Basically, it was specifically a bigger prize for teams that were using liquid methane. Zucrow had experience using liquid methane as propellant in testing. So because of the fact that it was more money, as well as the fact we already had advisors that had experience using that fuel, we selected that fuel without really looking at others.
If it was the same for money, we wouldn't have done nothing at all. We would have done with it. Yeah. Cool.
Back to the previous question about what's the most difficult thing. At least in my opinion, if you actually have nothing to start with, if you're starting from nothing, I think finding a good team is the number one. Because you can't do it alone, obviously. So finding a good team with diverse background is probably the best thing to get. Once you have that, then you can begin forming your team, deciding what your end goal is.
Yeah, if we didn't have a lab bottle feeding us, there's no way. What San Diego did, it was insanely impressive, the resources you all had. And it's impressive what you guys have out there. We're the bottle fed kids. Right? I don't want to say the headphones, but it's just hard. It's super hard. So, and you guys do it. Cool. All right, so I'm going to get into this. All right, so if I can ramble on, again, ask questions as much as you want. This is kind of an overview of how the reduced team started. Where we at? So what's the first slide? We forgot the slides. So we can start, guys.
Perfect.
All right, so here how we get started, what we designed, how we built it, how we tested it, and where we should go. Okay, so beginning. Look at that. All right, so before the beginning. So back in 2017, SEDS Purdue had 5 members. Okay, we had no rocket team. We were pretty sure. It was bad. Our NASA SL team, was embarrassing. We were so unorganized.
You led that one?
Yeah, I did that. Learn from your mistakes, and that's what I did. All right. So after I ran 2 teams into the ground, I said, let's do liquid rockets instead, right? I'm really glad I did. Okay. So I was doing homework one day in one of our study halls, right? I was on Reddit, of course, fetching to do homework. And then on our Rocketry, this came up, Farm Arts competition, and it's like, oh, this is really cool. So at the time, I had no idea what Zucker was. Zucker is our propulsion lab at the school. And so I found who SEDS advisor was because no one talked to this guy for like 5 years.
Yeah, because no one was doing rockets at SEDS, and that's what
And I said, hey,
really cares about.
You have a lab, can we do this? He's like, sure. Cool. So since you didn't say no, we started on it.
Yeah.
And so the Farm Arts competition was a 2-pound payload to 45,000 feet with basically an O motor. You won $50,000 for hitting the 45,000 feet with a bi-propellant rocket. You had an extra $50,000 you did nothing. So that's why we picked nothing, was because extra 50 grand. And of course, at this time, we're like, rockets only cost like $1,000. Like, that's awesome, right? No. Okay. Yeah, and Scott said, where can we get a $100,000 loan? Thinking that's a joke. It wasn't a joke. Okay, so the next slide. I think it's what I just said. Yeah, so we had a call out. We were expecting 15. We got 280 people in the room.
Yeah, I was one of them, just kind of sitting in the back.
And I was like, because we're like, and the thing was, is that we had booked a room like this size, and I accidentally booked a large lecture hall. So I'm like, oh god, this is going to be embarrassing. Like, these 2 people are going to show up to this thing, and we're like, hey guys, trust me, we can build this giant rocket. And we 280 people show up over 2 nights, and it was like, wow, people are really interested in this. And so we spent 4 months trying to optimize this rocket. We didn't get anywhere. Our advisor Scott's like, guys, you need a thrust, you need to weight. That's all you need. And of course, we're like, no, Scott, we need full trajectory simulation. No. And so we spent 4 months trying to do that, and we finally got our act together, and we started actually designing the rocket. So go to the next slide. So we realized, hey, functioning is a lot better than actually trying to get this super high-tech rocket. Yeah.
So when you said you tried to optimize it for 4 months, what were you doing?
Like writing optimization codes in like MATLAB and Python, trying to get realistic estimates for how much drag was going to happen over what trajectories and things, trying to simulate if we've got this much weight with this chamber pressure, this O to F, about how big the tanks are going to be, an estimate of the fluid system, all kinds of different stuff that then tried to compare. And then we would just compare that to Open Rocket anyway.
And like at that time, we're like, we're going to go to space. It has to do that, right?
We got a little ahead of ourselves.
Honestly, this is a little embarrassing. Okay, when I started this, I was a sophomore, and I said this out loud, and I'm embarrassed. I'm surprised when I say this out loud here. I said, we can just put less propellant in the rocket when we do the Farm Arts competition, right? We'll build the space rocket, we'll just fill it halfway up.
Yep, I remember that.
Guys. Yeah. So we got a 250 after so we didn't have any applications. We said, if you want to do this, great, you're on the team. So you have 250 people. How do we convince these people?
Those are the people that kept showing up.
Yeah, and so we had this egg launch competition. It was so stupid. But basically, the thought process was, if you like this enough to do a stupid egg launcher for 2 months, you're on the team. That gives me just enough time to figure out what I'm doing. Because I had no idea what injector was. I had never seen one in real life before. I had never seen a liquid engine in real life before. Okay, so I'm like, I need to figure out how to do this while they're moving off. Okay, hey guys, do that. And so we did that. But over the summer, we had our 50-person team. We had 20 grand from sponsors, and we had 10 o'clock meetings. Why is that significant? We had people living or doing internships in Peru. Okay. They were calling at 10 o'clock at night on Google Sites, like, hey, let's get this working. Right. Yeah, right. But yeah, we were, and people on the West Coast everywhere. One guy in Britain, he's now on PLD, actually, back there a few months ago. We were working on this all the time. Like, we put, probably 5 hours a day per team member, for the core team, doing this a day all summer. It was pretty impressive. So the next slide is the rocket. So the idea was to go to 50,000 feet after we got the code. Space isn't happening. About 100 pounds dry weight, 1,100 pounds, actually 1,125 because we thought we were that accurate, but we weren't. That engine with a 2.9 O2F, 4.2 mass flow, so about 4 pounds a second, flowing through small systems, pretty neat. 8.12 second burn was the official time.
100 pounds of dry weight, that isn't an estimate of what we thought we could do it in. That was our budget. That was, with how much total impulse we have and how efficient of a rocket we thought we could pull off. That was the total amount that we could possibly use and still actually reach the altitude. It's heavier than that.
Getting a rocket, a solid rocket to 40,000 feet, it's not, you can get effort to that. It's not an easy task. And all that is just a casing and propellant. right? Well, with a liquid rocket, you got to carry like check valves, maturities, actuators, all this stuff. There's a lot of plumbing involved. All those lines you saw, and even more lines you'll see from them in a minute, are stainless steel or some sort. It's a lot of weight. So getting an aluminum casing with a tip on it to 40,000 feet is hard. Doing it with an impulse, and that's what really killed us. If we had all the impulse in the world, yeah. But like, we had it very, 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 very limited. It was just possible, and what we did here, we calculated, it was going to be super, super, super sporty, and you'll see what happened next. So, next slide.
Ooh, do we have,
What's this?
The video.
I don't think it's a video. Is it a video? Go to the next slide. I don't know what that video was. Okay.
Oh, was that the injector video?
No,
We should show
that's
that.
later. That's later.
Okay.
It's later. Okay. So that's what we decided. So we brought this to our advisor. So I'll do that in a second. So basically, no avionics, parachute, helium. So basically, this is the engine right here. This is the actual propulsion unit. This is what we show off to people. We have our pressure, gas here, which is helium. We have our coaxial propellant tanks, some run valves and some fins in the engine. Okay. Why I say coaxial propellant tanks? Basically, we put our methane tank inside of our LOX tank. Why did we do that? Well, we thought we could save a lot of weight, and we did. We saved about 6 pounds, which on a 100-pound rocket, that's pretty significant. That's pretty good.
Biggest advantage we got from it is the fact we were having to make the methane ourselves and then float into the rocket. And so if we've got the LOX already flowed in, we don't have to then chill in the methane tank with the methane we're trying to create. None of that's going to be boiling. The LOX is going to keep it colder than its boiling temperature, so we don't have to worry about boiling off all that methane just as we're making it, having to worry about trying to catch up to that.
And the cool thing is with the densities and freezing points and all that stuff with LOX and methane, it just happened to be so perfect. Everything just kind of fit right together. So it was really, the question?
You did helium, so you wouldn't have to have pumps, right?
So yeah.
Yeah, so doing pressure, so basically the two standards for a student level liquid rocket is you either do pressure fed of some kind where you've got a pressurized gas that is with a regulator that is constantly pressurizing the tanks as it flows into the engine. The other one is a blowdown. Basically you pressurize your tanks initially to a much higher pressure. You don't actually have then a pressurized gas tank on the rocket, and then basically the pressure in the tank goes down over the course of the burn. Your flow rate is obviously decreasing over the course of the burn, and so your thrust is decreasing over the course of the burn, but then you don't have to worry about constantly supplying that pressure and gas to the tanks.
Yeah, and originally we thought, oh, we'll do a regulated system. And technically this is still a regulated system, but that also changes too. Yeah, so we're super excited for this. All right, we spent like 3 months working on this CAD model. We're like, Scott, look what we did. You know what he said? He's like, yeah. I said, look at it. He's like, it's a cartoon. And that really occurred to me. That was one of the first lessons I learned in this project, and kind of a life lesson, kind of tangent, is that you can have all the drawings in the world. That means great.
Yeah, it makes sense.
It's great. You have drawings, right? You can go CAD. You could have done this in Photoshop. You need CAD. And so that kind of was defeating. I really felt sad about that. I'm like, oh, but it was true. It was a CAD model. And looking back at it, that was more of a motivation. Like, oh, he's trying to tell us, like, don't stop at this. You haven't even begun yet, which I thought was really helpful. But some fancy, I don't ever use transitions, but I thought this is appropriate. So next slide. Look at that. Ooh, yeah, look at that. Wow. So that's Boomy Zoomy now.
The name is Boomy Zoomy.
Oh, you said about that. Rocket's name is Boomy Zoomy. Okay. Reason being is that we spent forever trying to find a name for this thing. We didn't want a serious name. We wanted not a super fun name, but like we didn't want to be like another, like Titan or whatever.
We could never agree on a name.
We never agreed on a name.
And then one guy said,
you call it Boomy Zoomy, and I said yes. And another little piece of it, which is not really the burning part, when I first started working at Zucro, a PhD student I was kind of helping out with, I was talking about the liquid rocket team. I didn't tell him I led it. He's like, yeah, those kids are a bunch of circus clowns.
Is that Tristan?
Yeah, Tristan. And so, Boomy Zoomy I thought was a little more circusy too, so I'm like, I'll keep it there, because we're a bunch of circus clowns. But we have to do stuff that's kind of neat. So that's the rocket. Again, it's just a picture, thankfully. I'm going to go over manufacturing details in a second, but pretty much it's all aluminum. And actually, we can go to the next slide, and we can start talking about that. I don't know why.
Are these videos? Is that what's taking so long?
Can you like exit out real quick?
Let's see what is that?
Can you like go to the side thing? Actually, I'm there.
Oh, hey, it's a picture.
Oh, it's pictures. Yeah, that's us.
Oh, it was my CAD that we skipped back over.
That's right. Yeah, that's part of the team. Cool. All right, we go to the next slide. Sorry about that. You see, it's not very big. It's pretty tiny compared to what it really needs to should be. That's the manufacturing slide. Let's go for that one. There we go, manufacturing. Okay, so I spent way too many slides on this. So I'm gonna kind of go over this real quick. Okay, so basically how this is gonna work. I'm gonna start from the top, work my way down because the stuff down there is a lot cooler. So one thing with our nose cone is that we really wanted to try to get other departments at Purdue to work with each other because we're all kind of like separated from everything. And so one of the things we did, we went to our Polytechnic school and they have seated a giant composite-based degree where people only do composite layouts, they only do composite research. It's like, hey, they do stuff, why can't we do stuff like that? So he said, hey, fresh search regard, can your class make this? And so part of this senior design project, so they need to make a new P head, and make a train, make all kinds of things. One of the parts is that next slide, actually, real quick, and we'll go back. They bought this aluminum, which is nice. They machined everything out. They got all the curves right. And they actually manufactured it for us. So this is part of our composite lab. It's like I don't know how many square feet it is. It's big though. I'm not a composite person. All I know is that the things we got, which is the next slide, were super nice nose cones from them. We think, oh, it's the nose cones, fiberglass nose cone. We're happy about this because we're able to actually do things with other colleges. And things like this helped us out when the air department right now is saying, hey, should we take this rocket we're doing right now and turn it into a capstone design? Okay, and this is kind of a thing that showed me, hey, listen, we not only use an air department capstone design, we can get other departments and use all of the university instead of just a subset. Because if we get all the university, it's more money for us, right? And it helps everyone else out. Because the students, instead of making another clipboard for this 15th time, they make a nose cone that's going to fly on something, which is kind of cool, right? So it's kind of all a big encompassing thing we're trying to do. Next slide. Oh, and the things that were in the other slides before that, we use standard hobby stuff. The top half of the rocket is exactly like a high-power rocket. There's nothing. It's RC3 altimeter, it's the same parachute, same everything. There's nothing different. It is like...
You don't need to reinvent the wheel there.
Yeah, don't reinvent anything, don't need to reinvent that. As manufacturing, we logged 716 hours at our machine shop. That's student hours. So we had somebody in our machine shop from 8 to 5, pretty much every single day all of last semester, working on it.
Yeah, it was pretty crazy.
Yeah, it was. There's one person that they had no idea how to run a lathe, and I honestly do think they can run better than lathes, not better than some of the TAs can, because they just were in all the time. Yeah. Which is really kind of neat. All the welds were done by professionals because pressure vessels are not like, you can't just weld a pressure vessel. You have to get it by a certified person because things go up. So welds were done by other people.
And then the injector was done by professional machinists, but everything else was machined by the students.
So 95% of the rocket's aluminum, which is a lot. The reason we did this is because, okay, at the time, we had hardly any money, and we know composites are expensive and complicated. And none of the fiberglass tubes from the hobby rockets actually matched up to the tank size we needed, which in retrospect was a terrible idea. We should have just had a transition and made the whole rocket like fiberglass, like standard size and whatnot. No, we went to the idea was, okay, we had everything one size, maybe most aerodynamic and whatnot. So we're like, okay, we'll use this. So thought process was, well, we have a machine shop, we have a ton of people, and aluminum's cheap. So the idea was we can make everything ourselves. It's not the most efficient. I would not recommend you make the whole thing out of aluminum. That is a bad idea. Because, it's a bad idea if you can't get super fancy machines to actually get walls and things down really fancy. We didn't do any fancy like Orion has, like all those like triangles everywhere. It's like pipe, machine the OD to a little bit, and that's it. Like that's it. That's all the complication there is to that. But it was cheap. The whole rocket, that thing that actually to fly in the air was only $2,000. Okay, the ground support equipment is worth about $75, but the rocket is only $2. So it really, I mean, that's cheaper than some of like rockets at NASA SL are, right? And so it's all dependent. So, all right, next slide. Yeah, so this is pictures of machining. This is our end of our tank, and that's Robert Grimar, our manufacturing lead. I don't think you have to measure anything.
He's just posing, yeah.
I think he's posing in that picture. But in our machine shop, we have 2 CNC lathes, 3 CNC mills, and a 5-axis CNC. And so we utilize everything but the smaller lathe, which is kind of neat. But really, it was cool because people had no idea. So like the freshmen and sophomores, right? They didn't know the fluid mechanics or the thermal stuff to really be useful in like the engine team, but they could, like Eli. But we put Eli in a machine. He could learn how to machine things and learn how to cam and all that other stuff. And as he's machining things and going, what idiot designed this? This is terrible to machine. When he's now, a junior, senior designing stuff himself, he can say, okay, we're not doing what these guys did. I know how to machine things now. I can look at things in a different way than they were able to. Because let's be honest here, not a lot of people machine. It was like one guy in every team, but like we all need to know how to do that. All right, cool. Next slide. Next slide again. So that's our fins. Our fins are kind of weird. They're basically like an 1/8-inch piece of sheet, bent almost. We machined it out of a bar. Long story. But it was really wobbly, and we're like, hey, well, if we bolted our fins to this thing, we could make a giant T-beam and use that to connect the engine to the rocket. So we did. And so we have like super light struts on there, and it was kind of an accident, but it worked out well for us. And that's Robert again, holding our mid-air frame. You can't see all the detail in here, but like this is cut out a little bit. This is a recept in there that's tapped everywhere. It's really neat. We did it like this is because it's in here, all filled with plumbing. And we need to be able to get in there and turn things and like adjust things. So we don't have those giant holes on the side. Also for weight, but in reality, so we can actually operate and use the equipment. And we're dying. It was hard. It was a lot, right? And after all that, we were just there for an ungodly amount of hours, and now
Make sure you've got check valves to prevent your fuel oxidizer
That's
from
the
doing
next
what you need.
Yeah.
And so basically, it was just then, helium regulators in order to regulate the helium supply down to whatever pressure you want to have it in your tanks, and then a valve of some sort in order to be able to actually turn it on and start flowing the helium.
that's kind of how do we use what kind of system we use for helium. So originally I ordered a paintball tank, and paintball tanks can't work. They're fine, right? It's a DOT certified air vessel. That's cool.
It's got
Or
the
pressure,
money.
Problem is though, we got the tank, right? I opened the box, I'm like, oh, the tank's really big. Okay, I'm looking at this and looking at that, I'm like, oh, this isn't gonna work. And so it turned out like some stupid little map error really messed that up. And so I went out in our trash can and I found another tank. It's from Luxfer gas cylinders. It's basically a firefighter's oxygen tank. And it happened to fit in the rocket. So I'm like, that's the one.
That's one of the nice things about being at Purdue with Zucro is we basically got to go through Zucro's trash for valves and things, and we found some nice valves. Most of the valves that you saw on actually almost every single valve you saw in the test videos, those were all scrounged from just the storage containers that Zucro was just putting all the stuff that didn't care about anymore.
2 questions. One, how did you activate your valves?
Yeah, so basically you have, they're called solenoids. It's a little magnetic switch.
Yeah.
You supply, like, basically your whatever your muscle pressure is. We're using nitrogen gas at 100 psi. So we regulate that down from our bottle pressure with just a manual regulator set to 100 psi. You'll generally want to have some kind of reserve tank such that you've got a lot of volume of that 100 psi. So when you're activating a bunch of things at once, you aren't depleting that. If you take a look at Colossus outside, they've got that little scuba tank that's sitting in the middle of their 2 tanks. That's what that is. And so basically what that does is you have the solenoid that then basically turns on to start flowing that nitrogen through it, and then that goes into the actual physical actuator for the valve. And that basically just has giant cavities on the inside that allow that nitrogen to flow in. When it flows in that pressure, it causes that actuator to produce the torque that is then translated through a shaft to the valve.
They come with a valve.
Yeah.
Okay, so when you order the valve, you'll want to order whatever actuators will come along with
And
it.
the second question is, I thought I caught this wrong earlier. You said the rocket cost $2,000 and the GSC was $75,000.
No, so we didn't pay. So everything you see here was bought in $33,000 cash.
Yeah.
We scrounged about 40 grand worth of stuff out of the trash can.
Yeah. And most of that was just
Or
all
trash can storage units. Yeah.
And so when it comes to all the testing equipment, you need the DAC, all the different propellants, the valves and everything you need to just get the propellant safely into the rocket. That's a lot more just total raw equipment than you're actually going to include in your rocket to run.
We probably have time for one more question. So, yeah, in the back.
How did you go about asking companies or getting sponsors for that 30%?
So we asked a lot of companies. No one responded to us. I guess our team is just really bad at getting company
Very
sponsors.
bad. Very bad.
All of our sponsors were getting, so one sponsor was our advisor's company, okay, which helped out a lot. And the other one was Norman Filter because we're like a large percent of their customer base. And so,
Zucro is, yeah.
Yeah, so I mean, we didn't really get any sponsors. All that money we got was from those 2 companies.
Thanks to Scott.
Yeah, thanks to Scott. And so we just didn't, no one responded to our sponsorship emails. We didn't even get like a no. And then our business lead, he sent the letter to Virgin Orbit. He said, the first thing it said was, hello, SpaceX. And so that was kind of like an overview of our business team. We're an engineering school. Okay. All right. That's all the time we have. Thanks for all. We're leaving just yet. Sandy, you guys want to do your guys' stuff?
Yeah. So we'll be here for the rest of SpaceVision. So if you guys have any questions, feel free to corner me and Chris and just ask us whatever.
Yeah. So we'll go on to the next section here.
Before I start, anyone just stand up and shake it out. Like,
Yeah, it's been a long time. Yeah. And if you're on the floor, there are some seats opened up, I think.
Hey guys, we're gonna start again. So right now we're gonna transition into the more UCSD talk. We're gonna go over the Colossus test stand. Andrew's gonna go over what's called a PNID, which is just how the plumbing is broken down. So it's gonna kind of answer some of the questions that you had about how the pressure is actually pressurized through the tanks and how that kind of works. And like a test stand and an engine, an actual rocket, the architectures are very similar, but obviously the mission requirements are different. And we'll touch on that a little bit.
Cool. Yeah, so this is engine testing basics. I promise by the end of this presentation you'll know the basic components of what you need to get started with liquid propellant rocketry so that you don't kill yourself. You still need to do the analysis and make sure you buy the right components, obviously, do the fluid dynamic calculations, but that can easily be found in a textbook. And if you have questions, you can come to me afterwards. So this is a rendering of Colossus. At its core, it is two very large tanks and a bunch of structures that allows the engine to output thrust and us to read that thrust.
So these are the tanks back here. That's where the engine gets mounted.
Yeah, so real life picture, and then I think we have a video of the hot fire.
Yeah, play the video.
Before I go into this mess right here, I'll show you a video. There's no audio, so please bear with us, but yeah. And the exposure kind of sucks. Please pardon that as well.
So this was back in June. It was the first time we actually hot fired. We had done like 5 cold pulls beforehand. We're in the Mojave Desert. Ran pretty late in the night, as you can tell.
How loud was it?
Pretty loud.
What's your ignition system?
Solid rocket booster, stuck it, and then once it ignited, it popped out. Cool. So, all right. So this is our PNID. It's divided into several different subsystems. What you really need to worry about, sort of right now, are the orange lines and the red lines. So the green lines are, if you remember, Kyle said earlier about the actuation pressure you need to turn those valves. That's what the green lines are. But those aren't as important as the orange and red lines. And I'll go into detail, like I'll start from the top and walk you through what each component is there, what it's there for, etc. So, picture. Okay, orange lines are pressurization. So, as the name implies, we need, for pressure-fed rocket engine, you need a feed pressure. And generally, it'll start from a gas bottle. And we chose gas bottles at 2200 psi, nitrogen, kind of see up there. There's 2 of them on there. We actually use 3? 4?
2 for the press lines.
Okay, yeah, 2. So that's correct. Just a quick note on what all these symbols mean. If you see a PG, pressure gauge, so as the name implies, it's an actual reading that you can read. It's an analog reading. PT, pressure transducer, so it converts pressure to an electronic signal. Usually it's a 0 to 5 VDC output that you can calibrate and you can read it on a computer monitor. So yeah, there's 2 nitrogen bottles there for the 2200 psi. So we need to get it down to what our tank pressures need. So it's right here, fuel 1350 max. Usually it's going to be sitting somewhere around 600 to 800, depending on what the engine needs, but obviously we need to regulate it down. So the simplest system, discounting all of this stuff, is you can just put a regulator there and call it a day. It's not a very safe system, but it would work. So to make it safer and to actually make it a viable data acquisition tool, we have a lot of different add-ons we put on there to make it an actual working system. So the regulator takes nitrogen at 2200 psi, and as the name implies, it reduces that pressure down to, let's say, 800 psi. There are several different types of regulators, as Kaufman previously mentioned. There's simple hand ones, so you just turn the handle, and the more you turn the handle, the higher the pressure output is. However, we chose to sort of have a slightly different system where our primary regulator is actually something called dome load. So there's a hole in the top of the regulator. The more pressure you feed into that hole, the more it pushes down on the diaphragm, and the more outlet pressure is left through. And generally, we like to do that because handles can start vibrating during hot fire, and they can start slipping, so you lose your pressure setting. So what we do is we can ensure that our dome load is constant by sealing it off with a valve. So that's how we ensure we get constant pressure. So this is dome load. But dome load needs that pilot pressure through the top. So we hook up a hand loaded regulator like this. Sort of a closed loop system, kind of. We bleed off main pressure from our bottles, and we use our hand load regulator to indirectly control our output pressure of the dome load regulator. I know that's sort of a mouthful, so does anyone have any questions about what I just said? Cool. All right, so now our pressure is correct. It's outputting at 800 psi. We have pressure transducers to measure the outlet pressure, as well as pressure transducers to measure the inlet pressure. Pressure gauges as well. And we come to a main pressurized valve right there. And that basically gates the nitrogen from entering the tank. So standard procedure would be we would open the bottles, we would set our regulator pressure, and then we would open this valve to allow the nitrogen to enter the tank.
I do want to give some context. So obviously, like up here is all just nitrogen, pressurized nitrogen, and the way that the P&ID kind of split up is on this half is all oxidizer, on that half it's all fuel. So you can just look at like any half, and at least for the main propellant lines, it'll be exactly identical. That's just to give some context into like what you're looking at. So you're regulating down that nitrogen pressure into the pressure that you need for your oxidizer over here, and same thing on the other half.
And if you need a copy of this, our designs are all open source as required by NASA. It's in public domain. So if you want to come to me afterwards, I can actually give you a link that bunch of documentation about how we went about doing this. So yeah. So that's the gist of pressurization right there. If you want to see the components up close, you can go up to Colossus right outside. And if I'm out there, I'll show you exactly which component is on here. But for now, I do have some pictures. This is one of the regulators. As you can see, we feed it with a dome pressure. It's not very visible, but if you imagine like a bottle right here and a regulator right next to it, it comes in through here and goes right to the top. The gas main pressure comes in from here, regulates down to 800, goes through, and is stopped by this pressurization valve right here. When we open this valve, the tank pressurizes. You have a question?
In that system that you're talking about right now, why doesn't the regulator that feeds the dome valve also vibrate?
Oh, so it does. But if you go back to the P&ID, once we set this pressure, we close this valve right here. So despite the vibration, even if this kind of dislodges a bit, this is sealed off now. It's like a closed system. So that dome pressure won't change since we set.
Oh, so the pressure there is constant. You've trapped it on.
Yeah, we trapped it in between the dome and the valve.
Very cool.
Gauge panel. This is just sort of my OCD. Like I wanted it to be sort of consolidated. You can just lay stuff throughout the system, but it kind of becomes a mess. You have to run around the system to try and get access to things. So we tried to make everything consolidated, organized. That's our gauge panel with all the pressure gauges. They're all labeled to be the same as what you see on the P&ID. So if I say PG, I don't know, like PG12 or PG, whatever, I know what I'm reading, basically. Back of the gauge panel, this is a little bit less organized, but yeah. So main propellant lines. So after this pressurization valve right here, we run into a check valve. As Kyle said, the reason why they're there is because we don't want any LOX boil off or any oxidizer boil off traveling through the system and going all the way to the other side and mixing with the fuel. That's very exposed to the atmosphere, and we don't want that to happen. So we have a set of check valves right here to make sure there's no backflow. And it's essentially, the check valve is literally something, sort of a small cylinder, the whole board through it, and there's a spring attached to a poppet. So it's usually set to a very small cracking pressure, so the spring constant inside is set to start deforming at 1-2 psi. So you don't get too much of a pressure loss over it, but the whole point is that once that 1-2 psi is gone, or if you have fluid flowing in the opposite direction, which would mean negative pressure relative to the direction you're going, that spring will slam shut and you won't get any backflow. It's a pretty simple system. It's a good mechanical feel system. What else? Okay, so after check valves, it goes to the tank. So yeah, we can now pressurize our tank, right? What if we want to depressurize the tank? So obviously we need a set of valves to open that we can let all the pressure out if we need to, in case of an emergency or in the case of we're done testing or something. So we have another port in the tank, and it goes out to this vent valve right here. So that is pneumatically actuated, so as Kyle mentioned, it's controlled by a pilot solenoid that delivers nitrogen to it. If we need to vent, press the button on the control box, and then that valve opens, releases all the pressure.
I do want to point out one critical safety aspect for all of this is, if you notice like this ball valve, almost every ball valve, these little trapezoids are filled in, which means that they're default closed. So if you lose your pressure, if you lose power to the system, they default close. The only exception to this rule is your vent valve, which is default open. So if you lose power, if you lose your air, it goes default open, which means if Colossus is sitting with both tanks pressurized and you lose power, your main line closes, your press valve closes, and you depressurize the system. So the system is now safe to approach, well, more or less safe to approach, because your tanks are no longer pressurized. So that's one critical safety aspect of engine testing.
Cool. So that's our vent valves. They're ball valves, fail open. However, let's say that doesn't work, or if the pressure just rises way too fast for us to have a reaction to it. Pressure relief valve is our mechanical failsafe. This is really important. Every single pressure vessel we design, whether it be in a rocket, test stand, factory, anywhere, should have an accompanied vent valve, pressure relief valve. No questions about it. You will kill yourself if you don't have that. And pressure relief valve is kind of similar to a check valve in design. They're not exactly the same, but they are spring loaded as well. And that spring is timed to crack at a set pressure. So I forgot what we have.
For Colossus, we have them set to 1440 psi.
Yeah. Which is, I think, the limit of our ASME rating. And generally, you would set that pressure relief valve to crack before your safety factor. So if you design your tank's safety factor 1.5, probably crack at 1.25. I don't know if that's a standard, but that seems logical.
Have you tested that?
What's up?
Have you ever tested your mechanical safety valves?
I think we have, right?
Mm-hmm.
We pressurized them all the way up to max, and they cracked, and it was super freaking loud.
Yeah.
I think everyone had to clear the building and wear ear protection, and you could still hear it vibrate.
You hear at least for hours, you hear 3 distinct pops. It pops 3 times, and it depressurizes from 1440 to 900.
A really important point is that once it cracks, it won't reseat until it's well below that crack pressure. So you have some margin, so it doesn't snap shut as soon as you go below crack pressure. So that's nice. So we have our tank now holding fuel or LOX, depending on which side you're looking at, and it's pressurized to what pressure you want to go at. This bottom portion is basically the entire liquid part of the system. So it'll be your fuel or oxidizer. Everything up here it's just gas, whether it be helium, nitrogen, etc. This is the liquid part of the system. So we have, okay. So we have our fill valve right here. So if we want to fill our tanks with fuel, propellant, we open that up and we fill from the bottom. Generally, the way you overcome gravity is through just some sort of feed pressure. Dewars usually come already pre-pressurized to around 250 psi, and that's generally enough to fight gravity and actually fill your tank. I I think for fuel, what we did was we used a compressor.
We use a pump.
Or a pump, sorry, to get that feed pressure so we can fill our tanks. Below that, main valve right here. And we call them main valves because this is the last sort of valve that gates past the engine. Once these open, there's no restriction on the flow path to the engine besides just tubes, basically. So these are point of no return. Once these open, test starts, and then we close them, test stops, obviously. What this thing right here, this is a non-standard symbol. We just sort of just drew it ourselves, but it's a cavitating material, and at its core, it is a converging, diverging sort of flow path that's precisely machined in size such that within a range of pressures, your mass flow rate will be the same, no matter how much you vary your inlet pressure. And that's due to Venturi effect. I think, Kyle, you can correct me if I'm wrong, but as the fluid goes through, pressure drops because like you're reducing the flow area. And as the name implies, cavitates, it will start to actually create bubbles, and those bubbles will lock down your mass flow rate, basically.
Yeah, it's the actual, when it comes to very specific physics involved, it's very, very complicated. But there are equations that empirically capture how they perform, and they are rather accurate when it comes to calculating what a set size and set pressure will yield in terms of mass flow rate.
So basically the geometry of this Venturi is dependent on what your engine mass flow rate is. So depending on the engine, you might need to swap out Venturis. Of course, you could always just say screw Venturis and just calculate optimum feed pressure, and if you trust your fluid dynamics knowledge in your system well enough, you can just say, okay, if I feel at exactly 860.25 psi, mass flow rate would be this. But having Venturis allows us to have some bandwidth to put it. Yeah, what's up?
Were those self-manufactured or bought?
No, I wish I had manufacturing talent to do that. There's a company called Flomax that will do it for you for how much?
I'm not sure.
Okay, it's relatively affordable compared to other components, but basically, like you give them your MDOT, your inlet pressure, your basically your parameters, and they'll draw a design for you, and they'll give you a quote.
We use the same company.
Yeah, they're a pretty cool company.
Flomax?
Yeah, Flomax. FLOW. The max has an extra X at the end. Max.
Yeah, don't try to make your own. It's not going to work, guys.
One of the big nice things about a Venturi is the mass flow rate you get through that Venturi is as long as it's choking, the pressure downstream of that Venturi can go up and down, but the mass flow rate through the Venturi will stay the same. So if you don't see the combustion efficiency you were hoping to see in your engine and the combustion chamber pressure is lower, you're not going to then see a higher mass flow rate through your system since you've got a higher pressure drop. That Venturi will keep that mass flow rate to what you've designed it to lift through.
That's pretty much it. We have a set of pressure transducers and thermocouples before and after the Venturi, because with data, with pressure and temperature data before and after, we can use fluid mechanics to basically calculate our properties. Like those are the two main data points that we need. Besides that, that's the main gist of like Colossus feed systems. We do have a purge system that it's pretty logical. Basically, when we're done testing, we'll turn off these valves and we turn on the purge system, and that's basically nitrogen full blast that clears out the engine. Any residual propellant that's left, we don't want it to be there, so we just and then I went into detail about the actuation lines as well. They're relatively low pressure, only around 100 psi. 180 psi. But yeah.
And that's where the other two K bubbles come in. So Andrew mentioned at the beginning there's 4 total K bubbles. So the two obviously for the pressurization lines, one for the pneumatic actuation, and one for the purge.
And you can see, just to reiterate again, pressure relief valves throughout the system. Not just tanks, but anytime you have like any pressurized area, even of just tubing that you think is in danger of overpressurization. So let's say if a regulator failed, I have 2200 psi full blast to the system now. The system is not designed to take that, so I need that pressure relief valve there, basically. Oh, interesting. Okay, I took this picture 30 minutes before the presentation because I procrastinated and I needed to make this PowerPoint. But this is a pressure relief valve that's on our system. If you go outside, you'll see this as well. Basically, tank comes up over here, and this is the outlet. It's sealed right now to avoid any debris from getting in, but if you want to test, we take off this, and if it needs to function, then it'll let through there. This is our main valve. It is a very big and heavy valve, partially due to its cryogenic rating. As Purdue mentioned, cryogenic generally implies super expensive, super bulky, and really high in mass, and just basically, they're hard to deal with. So
expensive.
Yep.
I think I remember last year we were trying to finish these up, and these valves were kind of late in coming in. And in our CAD, we just had regular 1-inch valves going, like without all of this, okay? And then, so when they shipped here, they were 100 pounds each.
That's what we thought they looked like
Yeah,
at first.
that's what we thought they looked like. So that's what it was in CAD. And they weren't like that in real life. So we had to, I remember I was like, crap. So my project manager and I, we went to Home Depot, bought a bunch of Unistrut, bought a bunch of different bolts, and we sort of created this support for, so it's a really pain in the ass process to sort of do. Swage lock, it's simple compression fitting, so it's even more expensive. Swage lock is like the Apple of plumbing. All their stuff generally is designed pretty well and functions really well, but they charge a premium for it. So, yeah. I would definitely recommend AN and switch lock. Yeah, there we go. If you're going above 3,000, 4,000 psi, you might have to use Conan thread fittings, but I doubt you will go anywhere beyond that. So, especially for amateur applications. But if you're in industry, you might see that. Do you guys have anything to add about fitting?
The swage lock, so Zucker really hates swage lock with a passion. It's only because our advisor got really irritated at a rep one time. But swage lock is really, like I said, it's super, super, super simple to use. Thing is, it's more of a, I don't know, it's mechanical. There's lots more little pieces that can break in swage lock. With the AN, you're actually bending the tube, and then that tube's connecting to the surface to that. With the swage lock, there's compression fittings, right? So you have things kind of on top of things, and things can break, right? Swage lock breaks a little easier than an AN fitting would. If it goes out and about. I mean, if you're making the fitting and just sitting there forever, no one's gonna touch it. I mean, yeah, I'm not an expert on this, right? But like, AN's definitely, we use it for everything. Even our 6,000 psi systems, it's not going anywhere. But if you get your hands on swage lock and you don't want to buy a really expensive flaring machine or flare many tubes by hand, it's pretty good.
There's two more that I can add to the list of recommendations here. One of them is called Seal Lock. It's made by a company called Parker. Basically what that is it's the same kind of, if you flare a tube so that the tube is flat and then that sits up against a fitting that has an O-ring in it. AN really doesn't quite cut it when it comes to things like 6,000 psi helium. Helium likes to leak really easily. And so with the Seal Lock, you get an actual O-ring seal up against a tube. Those are a lot more expensive than even the AN is. Seal Lock is expensive. And then another one, it's basically a variant on the AN fittings that includes a little O-ring in the front part of that 37-degree fitting. You can get those both from Allen Aircraft or from Parker. Allen Aircraft ones are really good and really expensive. Basically for those, you can get a really good high-pressure cryogenic seal because they include a little Teflon nose seal thing at the very tip that forms a better seal than just the metal on metal.
Swage lock works really good. So, yeah.
The biggest thing with like AN or Seal Lock is you have to get the tools in order to be able to flare the tube, versus with Swage Lock, I mean, you just have the ferrules with the nuts and you just tighten it down.
And the tools are expensive too. The die for an AN is like $600 with a 2-month lead time, And my first day at Sucro, I broke one. And so I had to go to my boss and say, I broke this. And he's like, you almost assist? And I said, no. He's like, it's like, oh, you're getting paid this month. And so, yeah. Fun facts.
General word of note, the fluid system portion will be the biggest part of your budget, without a doubt.
And sorry, most time consuming too.
Yeah. And so be prepared to shell out the big bucks if you want quality. You can always just, sort of have a little janky setup going that like you don't have to tell anyone about, but ideally, like fluid systems are expensive for a reason, and it's because you're literally the blood vessels for the system, and if it fails, then the whole system fails. So yeah. Any questions for me, you can come up afterwards on our website. If you go to ucsd.org/Colossus, besides the whole description, at the end there should be a link to our documentation. It's a really comprehensive package. NASA made us do it in order for them to give us funding, but it goes into detail, not just feed systems, also structures. Like so, our structures calcs, our sims, heat transfer calcs, stuff like that. So everything you need is there. It's there for you guys. So yeah, that's it for us.
Does anyone else have any questions that we can answer right now?
You'll be here after.
What's your next steps?
Sorry?
What are your next steps?
For Colossus in particular?
For your group.
Oh, okay. So we have multiple projects going on. One is the Vulcan 2 rocket, which is Jet A LOX. Target altitude of 30K feet. It was supposed to be launched during the Farm Wars competition, but classic aerospace, stuff gets delayed and pushed back. So we're hoping to launch that end of winter quarter. We're in the quarter system, but that would be end of March, or mid-March actually, at like the Mojave Desert. So we have that going on. Colossus is undergoing some upgrades. Right now, even though the system is designed to be biocryogenic compatible and compatible with a whole bunch of different types of fuel and oxidizer combos, we do have to make several little small upgrades for NASA to clear us to use with LOX methane. Include probably integrating a burn stack, so a pilot light. If you've seen on an oil rig, they have a little flame going. NASA wants us to do that, so we're in the middle of designing that. We're also making upgrades to our DAC. Our electronics panel, if you've seen out there, it is a very sort of intimidating thing to first try and get used to. So we're trying to simplify it and make it more robust. Anything else?
I'm not sure if you guys have heard about the Base 11 Space Challenge.
Oh yeah.
But one of the requirements for that are to do a full duration burn test of your engine. So currently Colossus tanks are sized up to 8 gallons, which won't be enough to do that mission requirement. So we're looking at putting in bigger tanks that aren't rated for the pressure, but with the capability of a turbo pump or a pump, you should be able to feed in an engine for a minute or however long you need it for a bigger engine. So those, yeah.
Are you thinking of having like a Colossus 2 that's bullets on Colossus 1?
Not exactly, but you bring in Colossus and just bigger tanks off on the side that you can just wheel in essentially.
Very cool.
Anything else? Cool. Thank you.